the corresponding mean square error for each one. So now, okay, so this is all the old forecast. Oh, sorry, that's from example 7. And now see if yn plus 1 equals 10.5 is available, and we want to forecast, see this one is available, or yn plus 1 available. Now we want to update these two forecasts here. So the first one, so update this two-step ahead forecast for n plus 2 by the one-step ahead forecast. So this is new one. So this is new, this is old. In forecast error for yn plus 1. Okay, so this is the one given right here, the new data. And this one is the old forecast here. And for AR1, we know pi1 equals negative phi here. So minus, that's plus. And then phi for this one is negative 0.5. So plus phi, so that's minus 0.5. And times the forecast error. And this one is the old forecast for yn plus 2. So our new forecast for yn plus 2 is 10.95. And the old one is 11.15 right here. So once you have data at yn plus 2, you can calculate the forecast error. Now for yn plus 10, the new forecast when yn plus 1 is given. So this is 9-step ahead forecast. This is new one. This is the old 10-step ahead forecast. Right here, 10.8, which is the mean. And minus pi 9. So for AR1, we only have one non-zero pi j, which is pi 1, and then everything else is 0. So this term is 0. See, it's still 10.8. So I think from last class, we know see the forecast just about the process mean if the value h is large. See now pi 10, so h equals 9 or 10. So they are large number for h, and then the forecast error, it's just the process mean. So the old forecast is 10.8, the new forecast is 10.82. Questions? No? This is the last. Yeah, this is the last one. Topics in this unit, forecasting. So prediction interval or zero mean Gaussian stationary YT. So if time series YT is stationary and each YT has normal distribution and the mean is 0. So YT is stationary, normally distributed, mean is 0. We can calculate a prediction interval. So why this is the edge step ahead forecast, right? This is the edge step forecast. Plus minus, okay, now this notation here. So this is the critical value or table value from standard normal. So this is standard normal, mean 0, and standard deviation is, okay, standard normal. this notation. So this is the value right here. This is alpha over 2. So it means from this point to its right, this area is alpha over 2. So if we call this 95% prediction interval, and then the alpha here is 0.05. So alpha 0.05, and then here the alpha over 2. So we have 0.025. And you can find this value from the table for standard normal. This is 1.96. For 95% prediction interval, so this value, the table value is 1.96. So this is for 95%. For 90%, so this value 0.05, right? So 90% alpha is 10% divided by 2, 5%. So 0.05 here. So this one is 1.645. This for 90% comfort interval. 95% comfort interval, this table value is 1.96. Okay. So forecast value plus minus, this is the table value times square root. Okay, now this one here is the variance of the forecast error, right? See this one here, square. Okay, so expectation of x squared is the variance of x if mean of x equals 0. So the forecast error here, mean is 0. So expectation forecast square just varies of the forecast. So mean, this is the prediction plus minus table value square root, or this is the mean square error. I think this is mean square error associated with the forecast of yn plus h, right? Okay, so forecast value plus minus table value times square root of mean square error. So this is the we call the prediction interval. Okay, so in the AR1 example, so this is 7. Sorry, this is all 7 here. Okay, so we have 3 forecasts, 1 step ahead, 2 step ahead, and 10 step ahead, right? And then we have the mean square error for each one. We calculate in example 7. So now we want to find a 95% prediction error for yn plus 1, 2, and 10. Okay, so for all 3 this, so see forecast error, a forecast value, 1 step ahead, 10.1 plus minus 1.96 for 95% prediction interval, square root. So 1 is the mean square error here. And 2 step ahead, forecast value in the mean square error 1.25, forecast value 1.33. So the mean square error here. And this is the interval. So you can see the interval gets wider and wider, right? Because the uncertainty is increasing for the large edge value here, for the long-term forecast. Any questions so far? So we finished this unit, and your test due tonight. I will send you homework. I think the homework 4, right? I will send you the homework for either tonight or tomorrow. About this unit forecast. And we'll start the new unit parameter estimation. And then we have now parameter estimation, I think, and then we do model selection, model diagnostic. And then after that, probably most of the time in class, we'll do examples in R. We're going to feed different models to real data. So I think this is the last unit. We have to do a lot of math here. So parameter estimation. So what parameters do we have for C? If you have time series YT. So for example, it's just general, it's stationary. So you have stationary time series YT. And what do you want to estimate? So probably you want to know the process mean, right? And then the process say varies for the ACF for this process. And then additionally, if you know this is a ARMA model, say ARMA PQ. So ARMA PQ, so this is a general formula. So we have P1, V1, YT minus 1 plus VP YT minus P. And then, so then we have the MA part. So theta 1, ET minus 1. We have theta Q, ET minus Q. Okay, and remember, you had this assumption it is white noise with mean 0 sigma E square. Okay, so if mean is not 0, you have to subtract mean from each Y value here. So from each Y value here, if mean is not 0, okay. So how many parameters do we have in this ARMA PQ model? Mean not 0. See, what do we don't know here? So mu is 1 parameter, right? We don't know. And then V1, we don't know. V2 to VP, and theta 1, theta 2 to theta Q, right? So PAR coefficient, QMA coefficients, and the process mean, and also the Y noise varies. So this one's I know too. So P plus Q plus 1 for sigma E squared, and plus another 1 for the process mean. Okay, so that's the parameters we need to estimate. And how about P and Q? Suppose P and Q are given, and we have to estimate P plus Q plus 1 parameters, right? And so at this moment, we assume we know P and Q. And then the next topic, and we need to decide the value for P and Q. So how do we know the order for ARMA P and Q? Okay. Okay, so first we do the estimation of mu, process mean, and then the process or the ACF rho K or gamma zero, the process varies. Okay, so suppose YT is stationary with mean, so mu YT, so if it's mu equals mu, and then ACV, okay, ACF, that's gamma K. ACF is rho K. So estimate the mu, the process mean first. So mu, we put a head here, so means estimate. So mu head, so the estimate of the process mean, okay, just the sample average. We just use sample average to estimate the process mean. So sample average y bar, so that's the sum of data from 1 to n. So n is the sample size divided by sample size n. So that's the sample average. So this is the estimate of process mean, estimator. Okay, and then so mu head, if the data is given and the mu head just a number, right? But mu head varies from sample to sample. So mu head is actually a variable. So you can calculate the expectation. So the expectation of mu head or expectation of sample average just equal to the population mean, right? So sample mean average is the population mean. This means mu head, this estimator is unbiased. And then, so we know the mean, so now the variance of this estimator. So variance of sample mean, so this is the sample mean. Okay, n is constant. So variance is second moment, right? So the constant you need square, so 1 over n squared. And then variance of x equals covariance between x and x, right? So this is the sum and sum. So now we need to calculate this covariance here. So this covariance, so you have, so n terms in here, n terms in here. So in total, you have n by n covariances here. See, y1, each term in here, say y1. So you have covariance of y1 with every term in here. So y1 and y1, y1, y2, y2, y1, y3, and the last pair y1 and yn, right? Okay, and then you do this for y2. So y2 has covariance with every term in here too. Okay, so y1 and y1, so that's varies, right? y2 varies. Yn, that's varies. So you have n varies, what we call this gamma zero, right? Because this is stationary, so process varies a constant, so that's the gamma zero. So you have n gamma zero here, so n variances here, and then this term is the covariances. For example, y1 and y2, so covariance between y1 and y2, right? So we have this term is for covariances. Okay, so k from 1 to n minus 1. See, you have, so you, okay, so you have, see, you calculate here y1 and y2, right? And then for y2, you calculate y2 and y1. These two are equal, right? y1, y2 or y2, y1. So these two pairs, the covariance are equal. So you have 2 here, 2 times. And then you just do calculate everything. So here. So you do y1, y2, y1 to yn. So this part, you do y1 with everything from y2 to yn. And when you start for y2, you do y2 with y3, and then everything into yn. Okay, now, so right here, see, for gamma 1, okay, when k equals 1, so that's gamma 1, right? So how many gamma 1s we have here? So we have y1, y2, right? y2, y3, and y3, y4. The last pair is yn minus 1 and yn, right? So that's all the pairs for gamma 1. The time lag is 1. So y1, y2, y2, y3. So y1, y2, this pair, y2, y3, and 2, yn minus 1, yn. So you have n minus 1, gamma 1, right? So it's right here, gamma 1. So you have n minus k, n minus 1, gamma 1. And for gamma 2, so for gamma 2, you have y1, y3, right? The time difference is 2, y2, y4, y3, y6. And then the last term is yn minus 2, yn. So you have, see, for gamma 2, you have n minus 2, right? So you have n minus 2, gamma 2. So we don't have gamma n. So the last AC VF is gamma n minus 1, which is just one term. So that's y1 and yn, right? y1, yn, that's gamma n minus 1. So the last one. So, okay. And then, see, the first term n gamma 0 divided by n squared. So that's gamma 0 divided by n. And then the second term divided by n squared. So this term here divided by n squared, so we have 2 here, we got 1n here. So we divided by 1n in here, divided by another n in here. So n 1 in here, 1 in here, so that's n squared. So this one, n divided by n is 1 minus k divided by n times gamma k, right? See, if we want to write everything together here, so k from 1 to n minus 1, and then, so you have gamma k, right? And then gamma k equals gamma negative k. So you have k from 1 to n minus 1, and then negative 1, so that's negative n minus 1. Okay, so that's the second term here. And the first term, gamma 0, so gamma 0 is right here, right? So this is a gamma 0. Okay, so now you write the two terms in one, so that's 1 over n. So sum k from negative, see right here, negative n minus 1 to positive n minus 1. So this includes the gamma 0 here, and then 2 times gamma k here. Okay, so that's the variance of mu hat. So this is just your estimate, right? And then you know your estimate is unbiased. And then you know the variance of your estimate. Okay. So the reason we calculate variance, because we want to get the comfort interval. Okay, so if you have stationary Gaussian time series. Mean is not zero, mean is mu, right? And then the y bar or the mu hat, the estimator of the process mean. Okay, so has normal distribution, so this mu hat is a variable, right? It has normal distribution. So this normal distribution, the mean is the process mean, mu. And the variance, okay, here, you see, this is the variance of mu hat, right? We just calculate this one. That's the variance of mu hat. So mu is the mean. See, mu hat normally distributed and it's mean. So we know the expectation mu hat is mu. Variance mu hat is this variance, right? So it's normally distributed. And then the 95% confidence interval for the process mean, okay, it's the same. Again, the estimate plus minus, so 95%, 1.96 square root. So this is the variance, right? Or the whole square root of variance is the standard deviation. So basically, so the form, so you have your estimator plus minus 1.96 times its standard error. Standard error is square root of variance of this estimate. So standard error here is the square root of variance of the estimator. So this is a general form. And typically, when you have data, so you don't know the gamma k, right? And then you have to estimate before you can calculate this confidence interval.
I'm sorry, quick question.
Mm-hmm.
What is that variance of YT?
Oh, here, that's the variance of estimator here.
Oh, that's okay, thank you.
Yeah, sorry. So that's the, okay, here is the EST. Okay. So this is the estimate for the process mean. You have estimate, and you got variance, and you got the confidence interval. Okay. So now we move to. Okay, yeah, we have two examples, and then we do the estimate for ACF. Okay, the first one. Okay, suppose YT is uncorrelated stationary process with mean mu and variance sigma squared. So find mu hat, expectation mu, variance of mu hat. So mu hat, for stationary time series, mu hat is the sample mean, right? Sample average. So calculate the sample average. So mu hat is the sample average. In the expectation of mu hat, so that equals to the population mean, right? The process mean. And then now the variance of mu hat. Okay, we need this formula right here. We need this formula right here, or either one, or you can, or you want to use this, that's okay. See, for this example, YT is uncorrelated. So uncorrelated means rho or gamma k see gamma k. If it's uncorrelated, this gamma k equals 0, right? For all k, see larger than equals 1. Or, how about put this? Right? So gamma k equals 0. For this example, yt is uncorrelated. So uncorrelated. Uncorrelated means no covariance, right? Or no correlation. Gamma k is 0. From like 1, like 2, and so on. So if you see the formula for the variance, so k from 1 to n minus 1, this gamma k is 0, so the second term is 0, right? And so this one just gamma 0 divided by n. And yt is uncorrelated mean mu varies sigma square, right? So this is a sigma square. So mean is mu, and then yt varies the sigma square. So the sigma square divided by n. Okay, so this is example 1. The answer for example 1. So these two formulas, so the either one is fine. They are same. Okay, so example 2. So now we have a MA1 process. So MA1, see, if mean is not 0, so we have to subtract mean from each term of yt, right? And then y noise, so theta is theta. So this is theta is negative 0.5. So now we want to find, okay, varies of mu hat and then the 95% comfort interval for the process mean mu. Okay, so first we find the estimate first. That's y bar, right? And varies of mu hat. So that's gamma 0 divided by n, first term, plus 2 sum k from 1 to n minus 1 divided by n here. We have 1 minus k divided by n and root of gamma k. Okay, so now, like I said, for ER1, MA1, you should know everything about like ACF, partial AC. For MA, you need to know ACF. For AR1, you need to know the partial ACF. So for MA1, gamma 0 is 1 plus theta square times sigma e square, right? And gamma 1 is, that's gamma 1 is theta times sigma e square. So in here, in gamma k equals 0 for all k is large. k equals 1, you have gamma 1, right? And then for k equals 2 to n minus 1, gamma k is 0. So in here, we have just one term. So that's n divided by 2. Two over n times 1 minus 1 over n times gamma 1, right? And then you can plug in. So 1 plus theta squared sigma e squared divided by n plus 2 divided by n. And right here, yeah, 1 minus 1 minus n and theta sigma e squared. So this is the variance of mu hat for a MA1 process. In 95% comfort interval, so we have the estimate y bar, right? Plus minus 1.96 for 95%. Square root, so you put the variance of mu hat here, which is the one we found in here. So that's the 95% comfort interval for mu. Questions? Okay, so next we want to estimate. Okay, so this is the ACF. So rho k hat estimate of rho k, right? So this one here, so the divided by n, so the top divided by n is gamma k. And then the bottom, this one here, divided by n is gamma 0. So rho k equals gamma k divided by gamma 0, right? And then we put a hat here. So rho k hat is gamma k hat divided by gamma 0 hat. So gamma 0 hat, this is on the bottom, and gamma k hat is the sum divided by n. So yt minus process mean, yt minus k process mean, and we sum from k plus 1 to n. Okay. So this is the estimate. And then in general, our sample ACF is biased, unfortunately. But its expectation of rho k hat not equals rho k, so this is biased. So our ACF is biased. So you have to know that. But asymptotically means when you have large sample size, n is very large. If you have large sample size, and then so the limit of this expectation equals rho k. So we call this is asymptotically unbiased. So rho k hat is biased, but asymptotically it's unbiased. So you have to have large sample size. So you have large sample size, and then the rho k hat is unbiased. Your estimate is unbiased. So unbiased means it doesn't overestimate or underestimate the rho k, the process ACF rho k. Okay. So there's one thing you need to know, so we don't do any proof. You just need to know the result. So if you have IID or white noise, so mean is 0, IID stationary time series, mean is 0, variance is sigma squared, IID and no covariance, right? So you know mean, you know variance, and gamma k equals 0 for YT. Mean of YT is 0, variance of YT sigma squared, covariance of y by t. So where the gamma k equals 0. Okay, and then the estimate rho k. So we have rho k hat, right? So at like 1, that's rho 1 hat. At like 2, rho 2 hat. So all the estimates are approximately IID, so they are independent, identically, normally distributed, and the mean is 0. Because for yt, okay, for yt, we know yt mean is 0, and then variance of yt is sigma square covariance yt minus k equals 0, right? And auto covariance 0 correlation is also 0 here. So the estimate rho 1 hat, rho 2 hat, so all the estimates are normally distributed, they're independent, and then so the mean of each one, so this is asymptotically, mean of each one equals the process of rho k, so which is 0 here. So rho 1 is 0, right? So rho 1 hat is normal distribution, has normal distribution with mean rho 1, which is 0, and variance just 1 over n. So this is why when we use the ACF plot, so the sample ACF here. So sample ACF, basically this is the rho k hat. And the k here. If you have a IID time series or you have white noise, and then so that's 95% confidence interval for rho k. Okay, so if you have white noise, for example, or IID is stronger. So if you have white noise, rho k hat is normally distributed with mean 0, variance 1 over n, right? So mean 0, variance 1 over n. So the 95% confidence interval for rho k. So for each rho k, the 95% confidence interval. Okay, so the 95% confidence interval was confidence interval for rho k. If yt is white noise equals 0 plus 0 is the mean here, right? And variance 1 plus 1.96 times variance 1 over n. So now you see in R the ACF plot. So the two dashed lines. So this is 1.96 times 1 over n square root, and this is negative, right? And so this is 95% confidence interval for rho k. Okay, so now once you have say here or here, something like this, you can see if this rho k hat is significantly different from 0, right? So this is why the ACF plot, you can read each line is significantly different from 0 or not. Okay, so this is the estimate. So this is the first section in this unit. So once you estimate the process mean, and then the series ACF or ACVF, so the next so the section 4.1 just in general for any stationary times just with mean mu in ACF rho K. Okay, and then section 4.2. So this is just for ARMA PQ. So just for ARMA PQ model. And then so for this model, suppose so like say P and Q are given. So you know this is AR1, you know this is MA1, or you know this is ARMA1, ARMA2. Okay, so you know P and Q. And how do we estimate the? So we have a P AR coefficient and Q MA coefficient, and then this is the Y noise varies, right? So how do we estimate? So that's P plus Q plus 1 parameters in the model. Okay, and so in here we assume the mean is 0. So when we have times YT means not 0, and then you estimate mu by the sample average, and then subtract this from your original times just YT. And then you feed, okay, if you call this XT, XT, and then you feed a RIMA to XT. So this is ARMA PQ. And the XT will follow this form here. So you mean at 0, you estimate mean first and subtract from YT. Okay, so and then in here we just assume mu is 0. So in here we assume mu equals 0 here. And so in this section we want to estimate the P plus 1, P plus Q plus 1 parameters for given data Y1 to Yn. And then we have 3 methods to do this estimation. So the first one is called method. Okay, that's a method of moment. So method of moment. So that's MOM. So this method is good for MA. So this So this method is good for AR, not MA, not ARMA, just for AR. So this is good for AR model, ARP, not good for MAQ or ARMA PQ. Okay, and then we call least squares estimation method. So least squares, you can use this for all AR, MA, or ARMA. And we have maximum likelihood estimation. Maximum likelihood estimation is the one commonly used in estimation for AR, MA, or ARMA. And this is the default method in R to find the parameter. To fit model, this is the default method in R. So we have 3 methods. And then your Walker estimation. So this belongs to the method of moment here. So basically, this is the method of moment estimation. And this is just like self-good for AR, right? So we use your Walker estimate the method for AR model. So see ARP. So this is just for ARP model. Okay. And then means we do one method moment. So you Walker for ARP. Okay. So I guess we'll do this all the detail on Thursday. So today, as before, so we do about our lecture, and then we have 15 minutes for questions. So Well, if you don't have any questions about, you don't have homework, right? Or maybe a homework problem and problem from your notes or test, anything, any questions. So if you don't have questions, then you're free to go. And I see you on Thursday, and I'll be here until 12:15. And then also we have office hour today from 2 to 3. So typically we have about around 3 students during the office hours. So visit the office hours. So I hope if you have questions, you can come to the office hour. If you're not available,